Welcome grade 12. So another beautiful Tuesday, actually it's a Thursday today, beautiful Thursday afternoon, and you are with me, Tobile Nkosi. Thank you so much for joining the show. I just want to send a big shout out to Liberty, and thank you for the Tenfold education app. Please do download that app and you can send through all the questions. All the questions that we do have today did come through that app. So remember, be specific if you want to send me the app. Send me the questions. Like Mbali has said, tomorrow you are writing your final physical sciences paper, which is paper number 1. So I'm going to help you revise on actually how to ace that paper. A few tips coming from me to you. Number 1, when we talk about multiple choice, my darlings, always make sure that you have to have a reason why something is true or why something is not true. If multiple choice was pick the correct one by guessing, then it would be choose the correct one by guessing. Multiple choice means you need to calculate it. And also remember, if you are very strong at a certain section or topic in paper 1, make sure you ace that certain section. For example, if you're good with work, energy and power, get 24 out of 24. If you're good with electricity, get 24 out of 24. It is really possible for you to get a level 6 or a level 7 by focusing to what you want. Another thing that I've actually noticed with you guys, you tend to not read what the question actually says. So what I've been telling my kids, once you've answered the question and you've got your final answer, see what the question actually, the answer that you have, and see that it refers back to what the question has said. If the question said calculate currency and your final answer is talking about resistors, then you have a mistake somewhere. So remember, always go back to see what the question had actually answered. Remember to have your SI units. You do get a mark for that. You do get penalized if you do not have that. Make sure that you know between your scalars and your vectors. You cannot make silly mistakes. Everything that is a vector requires direction. So as we are working today, I'm going to try, teach, go deep, give you tips, how to answer the questions, as so forth. So the first question that we have here, it's question number 6. I'm going to read the question, then we're going to analyze what the question says. So the question says, a laboratory assistant conducted an experiment to determine. So remember, when we talk about experiment, it talks about we actually did something and then we actually found results. Right? So when you're doing an experiment, you usually have a before and you have an after. When you're already reading this, you must already see what your before and what your after is going to be. That is what we call an experiment. Remember, sometimes they can say an experiment or they tell you an experiment was conducted and the table below has all the data that was collected. In this case, it was an experiment and we did the experiment to determine the frequency. Already when you see frequency, I want you to think Doppler effect. Frequency of a tuning fork. Now, I know most people might not know what a tuning fork is, but just like for argument's sake, John Fredericks actually came up with this thing called a tuning fork. So what a tuning fork actually does, it's made of 2 prongs and it's actually, they usually use it to tune musical instruments. So sometimes you pick up a guitar and it goes and it sounds really, really nice. And then after a couple of months without playing it, it goes boing, 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 boing. It means that the frequency of the strings are out of tune. Right? So what happens is they use a tuning fork to actually put the strings back into order, and then you have that nice G, F, or A note, or however musical teachers do it. But a tuning fork is used to actually fix the frequency within musical instruments and make it sound right. Already we are talking about frequency, Doppler effect, right? We're talking about strings, we're talking about wavelengths, and so forth. So that's what a tuning fork does. So the tuning fork is set on a vibration and is mounted on a stand as shown in the inserted sketch. So here's my tuning fork. He then moves towards and then he moves away from the tuning fork with a detector which records the frequency of sound emitted by the tuning fork. I want us to go a little bit further. Now remember, when we talk Doppler effect, it's either the ambulance, I'm going to use the ambulance. Think about the tuning fork as your sound source. Think about the ambulance. If the ambulance is moving towards you, it sounds really, really loud. If the ambulance is moving away from you, then it goes wee, 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 because it's moving away from you. So already you must think, when this person moves towards the tuning fork, something is going to happen. If the person moves away from the tuning fork, he's also going to hear something different. You must also think, he has a detector. We have a tuning fork which is emitting sound, right? The detector is now what is your listener, and then your tuning fork will then be your sound source. It's what is emitting the sounds. We are there. So the graph below represents the results he recorded. The velocity of sound in the air is 340. Remember to not always guess this. Sometimes they do tell you that the medium is water, or it was a cold day or a hot day, so then the sound in the air will change, so be careful. Here we've got our graph that we're given. On my vertical axis, I've got observed frequency. I can see that my graph is a negative gradient. I've got 492 on this side, and then I've got 470. my time, I've got 5 and then I've got 20. And between these two times, I can see there is a change that actually happened. Now remember, when you have frequency moving towards you and we have frequency moving away from you, you are going to hear two different frequencies, right? As well as then that the time that actually moved. This is the assistance velocity. Remember, most of the time when we talk about velocity, we talk about the listener or the sound source actually moving and so forth. So this is the time that we're given. So let's see what questions come with this diagram. The first one says, name the phenomenon represented on the graph. Now remember, in physics, when we talk about phenomenons and laws and principles, is things that will never change. So one of these things, when you talk about the phenomenon of frequency and sound sources moving towards and away, we always talk about the Doppler effect. This is the phenomenon that we're talking about. So 6.1, the phenomenon that we're talking about is the Doppler effect. Make sure you write in capital letters, no slang language, the Doppler effect. That's the first one. Let's see what the next question says. So the next question says, does the graph represent the instant when the laboratory assistant was moving towards? Now they're written in capital letters, so you must either choose towards or away from the tuning fork, and then you need to explain why. In this case, we have a negative gradient. It will be moving away because the observed frequency is less than the sound source. It's moving away, negative gradient. So remember, you have to choose either between towards or away. The examiner wrote it in capital letters, so we're going to say away. And let's see, it is for 2 marks. So you do get a mark. Just want to double check the mark allocation, 2 marks. So you get a mark for choosing towards or away, and then you get a mark for explaining your answer. If it had more than 2 marks, I would say find another point. In this case, it just has 1. So away, so the observed frequency. The observed frequency is less than the sound source. Is less than the source frequency. So it is moving away from them. Remember, when you talk Doppler, it either sounds very loud or it sounds really soft. Negative gradient, it is moving away. So let's look at 6.3. We must write down the relationship. Remember, when they talk about relationship between two things, they either talk about, when you think about relationship, think about directly proportional, think about inversely proportional. What is the relationship between intermolecular forces and substances? What happens if this increases, this remains the same? When they talk about relationship, it's almost like a comparison between two things. What will happen if this or that is then changed? So we are told we write down the relationship between the laboratory's assistance velocity and then the observed frequency. Right, so as we're looking at this graph here, we can see that as the listener's velocity increases, remember it moves from 5 to 20, as the listener's velocity increases, the observed frequency decreases. The frequency started at 492, it decreases all the way to 470. However, the listener's velocity increases from 5 to 20. This was again for 2 marks. That is the relationship then that we have to mention. Remember to write full sentences. As the listener's velocity increases, we saw that it increases from 5 to 20. The relationship is the observed frequency decreases. The observed frequency decreases. This was actually a very nice question because most of the questions are just based on that. And I mean, because you have mathematics, you would be able to actually tell what is happening on the graph. So let's look at 6.4. It tells us, they're asking us, what does the x, let's look where the x is. It is on the vertical axis. What does the x, the intercept on the vertical axis, represent? It represents the frequency of the source. Remember, this is the observed frequency. That is the frequency of the sound source. That's what the x will represent. Again, we're going to write full-on full sentences. It is the intercept on the vertical. I would always suggest that you write full-on sentences so that the examiner doesn't have to guess or look for marks as they're marking. Represents the frequency. The frequency of the source. Okay, this was a lot of theory for Doppler effect. So we've done this one. Now we have a calculation. Now they're telling us to calculate the frequency of the tuning fork, right? So we know that we have the tuning fork. We don't know what the frequency is. We know what the observer and the listener have heard. Now we need to calculate the frequency of that tuning fork. So now remember, when you talk about the Doppler effect, I'm going to start it on a new page. We talk about the listener. We talk about the sound source. This is 6.5. Step number 1, I think it's for 5 marks. You always have to write a formula in physics. We've got F of L, which is the frequency of the listener, is V plus minus VL all over V plus minus Vs. And this is times F of S. Now, I just want to stress on the plus minus for both of them. This is how you actually need to remember it. If you have an ambulance that is moving towards you, it needs to sound really loud, right? This is how I want you to remember it. Your denominator must be a small number so that it can divide many, many, many more times in the numerator. Then you're going to get a big number. Big number means it's moving towards me and it sounds very loud. If so, then we use a negative at the bottom. If the ambulance is moving away from you, it needs to sound softer and softer and softer and softer, which means we have to get a small number at the bottom. So we add at the bottom and then we subtract at the top so that this number at the bottom does not really divide many, many times in the numerator. Then we're going to get a small number. Big number, we need to subtract so that it can divide many times. If we have to get a small number, we add so that the number is too big to divide many times in my numerator. That's how you remember it. Moving towards or moving away, that is then how we choose one as a positive and we choose the other as a negative. And also remember, if you choose the bottom as a negative or positive, then at the top needs to be the opposite of that. You cannot have a negative at the top and a negative at the bottom, right? You need to either get a very big one, a number, or a very small one, meaning it's moving towards or away. So let's calculate. So we've got the frequency of the sound source, but we need to find, we've got the frequency of the listener, we need to find the frequency of the sound source. Right? Now, let's just look here quickly. I want us to calculate something here so that we do not get confused. Now, remember, the velocity here was changing. So, to find one stagnant velocity, I'm going to say 20 minus 5. Let me just write it for us here. 20 minus 5 will then give me 15. Right? So that is then the change in that velocity that we have there. Final minus initial. So that's the velocity I'm going to use so I don't confuse anyone. The frequency of the listener, I'm going to go back to my diagram. Remember, because we are given a diagram, I'm going to use everything from that diagram. So there we are. We've got 495. This is the frequency that we heard. We must keep in mind that the velocity changed by 15, right? There was a change in velocity. This was the frequency that the listener heard. In this case, they said it was a detector. The detector detected this. So in this case, technically, our detector is actually acting as our listener. So the frequency that the listener, the detector, heard was 492. The sound in the air, which is the V, the speed of sound in the air. Remember, the speed of sound can differ from different mediums. It was 340. It's 340 at the bottom as well. And then here we're going to say a negative 15. And then times, I'm looking for F of S. Remember, the 15 is 20 minus 5. There was a change in velocity. That is then how I got that. Now it's just pure mathematics. I'm going to have 492 on this side. Let me not take chances to do that in my head. Let's use a calculator. I'm going to say 340 minus 15. I'm going to get 325. 325. All over 340. I am going to do this the long way around, times F of S. Remember, this is over an invisible one. Numerator times numerator, denominator times denominator. I'm going to have 492 is equal to 325 F of S, all over 340. I have to put this over a 1. If you have a fraction on this side and a whole number on this side, if there is an equation sign, you put the whole number on the other side over a 1. We're going to cross multiply that, multiplied by 1, this multiplied by 340. Can I please just work here so that everyone can see? So 325 f of s times 1 will remain 325 f of s is equal to, I'm going to multiply, let me just write it down, 492 and 340. You know, 325 f of s. I would always say rather do it the long way around than trying to do shortcuts. I'm going to multiply these two, so 492 multiplied by 340. I get 167 to 80. 167 to 80. I need to get f of s alone. The question said I must calculate the frequency emitted by the tuning fork. I'm going to divide both sides with the number that is bothering my f of s. Divide both sides by 325. This and this will cancel. I'm left with f of s on this side. I'm going to divide the answer I have here with 325. And then I'm going to have, let me just do that again. I said 356, 167, and 280. Divided by 325. There we are. That looks more correct. I'm going to have 51. Remember, I'm going to do it to 2 decimal places. Because the third number is 5 or greater, it will change the 0 into a 1. In physics and in chemistry, we always round off to 2 decimal places. So this will be 514.71. 514.71. Now remember what we were told here. There was a change in velocity here, and the change was 15. So in my final answer that I have from my frequency of my sound source, I'm going to subtract the 15 because there was a change there. They said it kept changing. If you subtract 15 here, negative minus 15, there we are. Then you get 499.71. Remember, always to 2 decimal places. So I'm going to have 499.71, and that is hertz. Hertz is the SI unit for frequency. So now we've calculated the frequency emitted by the sound source. Let's go down. Let's see what we have here. Then they continue to say, the laboratory assistant intends to use the tuning fork to produce oscillations. Now, oscillations is something that was introduced to us in grade 11. Oscillations is just a repetitive movement or vibration over and over again. For example, like sound source. Sound source is actually, if you were to magnify a sound source, it's actually moving back and forth, longitudinal waves that are just oscillating back and forth. So he's intending to use the tuning fork to produce oscillations, which is just repetitive. He's just repetitive movement with a wavelength, which is in meters for a grade 10 demonstration lesson. We need to use a calculation to determine whether or not the tuning fork will be suitable for the demonstration. Now, what do we have? We know that the wavelength that is required for this demonstration for the grade 10s is 0.71. Now, what do we need to do? We already have the frequency that is emitted by the tuning fork. We do have the speed of sound in the air, so we need to calculate the velocity that the tuning fork, the lambda that this tuning fork is actually emitting, and see whether we're going to get the same wavelength when we calculate it to what is actually required. So if we get 0.75 when we calculate it, then it is suitable for this demonstration. If we get something that is more or less, then it's not suitable for this demonstration. So using what we have, we're now going to calculate if we can find that wavelength. So remember, what do we have? We have the speed of sound in the air. We just calculated. In this one over here, the sound emitted, the sound source from the tuning fork. Let me use another slide so that no one gets confused. So this is 6.6. So remember, I'm going to use a formula. V is equal to F lambda. V is the velocity in the air or the medium. In this case, we were told it's 340. We know that the tuning fork is moving in a medium of 340. The frequency that we just calculated was 499.71. Remember, always to 2 decimal places. We need to calculate the lambda, or the wavelength, that this tuning fork is making, so that we can see whether it is the 0.71 required for the demonstration. It's just mathematics. So now I need to get the value of lambda. I'm going to divide both sides with the number that is bothering my lambda. In this case, it's 499.71. What you do on the one side, you have to do on the other side. 71, this and this will cancel. I'm going to have lambda left on this side. Let's see what we get. So I'm just going to take it as it is. Oh, no, I can't do that. So I have to say 340 divided by 499.71. Let me just make it a 1 there. Let's see. We get 0.68. Remember, it's a 0. So the 0 does not change the 8 into a 9. So it's 0.68. 0.68 meters. So the wavelength that the tuning fork will make is 0.68. Let's go back to the question. The question asked us, the lambda required for the demonstration is 0.71. Now, we must determine whether or not the tuning fork will be suitable for this demonstration. Wonk, wonk, wonk. No, it's not going to be suitable. I'm going to write here. Remember to always write. No, it is not suitable. It is not suitable. So you can continue to actually make your examiner very proud. You can say, you can actually put it in any way. Length. The wavelength produced by the tuning fork is less than the required wavelength. I want to see how many marks was this question for, and then just elaborate on it further. So this was going for 3 marks. Now, guys, remember, if ever in physical sciences or in chemistry, you had to explain why something was or is. For example, we must determine whether the tuning fork the wavelength will be enough or not. You cannot explain to an examiner and say, because. That's not an answer. You cannot as well tell the examiner, because the answer I got in 6.5 is not the answer that the question wants. No, the examiner wants to see that you understand that we're talking about wavelength, that the two wavelengths are now not the same. We also know that when the wavelength changes, the frequency will change, right? So remember, Doppler effect, it's either moving towards or away. And if we're doing a demonstration, we are doing an experiment, and we are trying to get certain results and trying to teach something, right? So if the wavelength is not really what we want, then that's not correct. When you're explaining something, tell the examiner, no, it is not going to work, or it's not suitable. And then because the wavelength that tuning fork is going to emit, you can even be spicy and say it's 0.68, whereas the demonstration for the grade 10, the wavelength required is 0.71 meters. The examiner that can see that you understand that it's 2 different wavelengths, that the demonstration will not work if the lambda is 0.68. That is then how you need to articulate your reasonings, right? And so forth. So hopefully we can do more of those, and then we can elaborate a little bit further. So that was the last question that we have for the Doppler effect.